Hey, this is Leach with Simpson Math, and in this video, I'm going to be demonstrating how to use Desmos to answer some inferential statistics questions, specifically the 1 proportion z interval and the 1 proportion z test. Since making a previous video, Desmos has added inferential statistics features to their platform, so that's what I'm going to showcase. In the previous video, you can show me, I will show you how I work that problem by hand using the 84 Excel in an internet applet. So this one is focused on Desmos. So let's first go over this problem. This says, I'm thinking about designing a new series of enamel pins for sale. I would produce these pins if I can be convinced that at least 33% of my current customer base is interested in buying at least one of them. I've since, random pause, distraction squirrels. This is one of our new pins that it's QD Pie. I just thought I'd want to share. All right. So let's say let's say I'm wanting to do that. Suppose I take a random sample of 50 of my current customers. I find that 21 or 42% of them are interested in buying at least one pin in this new series. We're going to make a 90% confidence interval estimating the actual proportion of my current customer base interested in buying at least one of them. Based on this interval, should it produce these new pins? Remember, I would be convinced to do this if at least 33% of my current customer base would be interested. So a little bit of assumptions here. Let's assume that my current customer base is large enough that the 10% condition is satisfied. Lol, it's not, but we're pretending here. All right, so I have the work here by hand. I'm not going to show you how or explain all these details, but because I did that in the previous video, I'm going to show you how we can use Desmos to get to our confidence interval of 30.52% to 53.48%. And notice that in this conclusion, we show that 33% is actually in this interval. So it is plausible, but it's actually plausible that I could have had a value under the 33%, which wouldn't meet that threshold. So then I shouldn't really make the new pins if I'm strictly following that guideline. I might be like, well, it's 30 to 53% of my base would be interested in buying the pin. Sure, I might, roll the dice and go with it. But according to my a strict interpretation of my goal, no, that's not enough evidence to say that more than 33% of my base would buy this pin. This sounds a little bit like a hypothesis test, and in fact, I'm going to cover that later, later in the video. But first, let's take a look at doing the confidence interval for this. All right, so I'm here on Desmos. I'm on a blank Desmos screen. Let me show you how we can get to the inference directly. So click on this, add an item. Scroll down and click on inference. You likely used this previously when doing the normal model math. So select that. Instead of doing probability distribution, we're going to select one of these buttons. Look at our options. This says inference for quantitative data. This isn't quantitative, this is categorical. The random customer either says that they would be interested or that they would not be. So then our options are inference for categorical data, a z-test for proportions, chi-square test for independence, or goodness of fit. Well, this is just going to be a z-test for proportions. I know it does say test. Desmos, when I spoke with Desmos, some people were wanting this to say inference or test, interval or test, but they're trying to limit the words here. So this will give us both a statistical test and inference. So go ahead and select that. All right, so here, this pops up an interface for us to put in our values. Let me open up my stuff here so we can remind ourselves that our sample size is 50 and our number of successes is 21. And so we have the wording here that says our number of successes is 21. So just key in 21, tab over or click on sample size, which is 50. Notice when it had 5, it did yell because that would be smaller than this. So that's a problem. Our sample size does need to be bigger. So this is the numerator over the denominator for our proportion. This is not a 2 sample. If this was a 2 sample test, you could toggle this open and add in those values, but this is just going to be a 1 sample test or interval and hit create test. All right. Nothing's graphing right now, so I'm just going to leave my solutions up here. In fact, let me go down and see what we got by hand. So I want to do a confidence interval, so I'm just going to click on confidence interval here. Let's toggle that open, and it defaults to 95%. Well, my direction said that I want to be 90% confident. So do you see how it's kind of grayed out? Well, that's anytime you see the gray writing, that is Desmos saying, hey, I'm wanting this to work. So I'm just going to put in by default this 0.95, but I want 0.9, so I'm just going to type in 0.9. I'm going to toggle back and forth real quick between 95 and 90, and I want you to see what happens here. So if I put in 95, notice how the interval gets wider. 90, it gets skinnier. 95, wider, skinnier. 95. What about if it's 99? Even wider. There's 95. Here's 80. Even skinnier. So it's nice how Desmos will adjust this relative width based on the confidence level. So in this interface, we can see that we should be 90% confident that the proportion of customers who would say that they would buy one of my new pins would be somewhere between 0.305 to 0.535. We do have our point estimate here in the middle, and if you can hover, it will provide the point estimate at 0.42. In fact, these values are calculated and live right here in these three dots. If you click the three dots, it'll open up, and again, we have our lower bound, upper bound with more decimal places. The point estimate, which is 21 over 50, which we already found. We can see that on the screen here, the 0.42. And then it'll even calculate the standard error, which I did over here in our work to get the standard error, 0.0698. If you want more decimal places on any of these, just like using the normal distribution, you can click on any of these buttons and it says export a snapshot to the expression list. So maybe I want to see the standard error a little bit better. So I can click on that and it will, this T1.stderr, that's just Desmos's coding for how it gets the standard deviation out of, knows how it labeled this test, T for test, T1. So that's just Desmos's coding for where this number lives. Don't worry about it because you don't actually need to type in that function. But that's Desmos's function. But take a look at this. This is the full world, not full because it's irrational. This is a whole lot more decimal places for our standard error from here. Why might you want that? Well, maybe you want to find the margin of error. There's a few ways you can find the margin of error. If you know by hand that we did 1.645 times, I can copy this number. Literally, I'm just going to copy and paste. Now I can get our margin of error here. Maybe you want to find the margin of error a different way. We can find the margin of error by, I'm going to put some returns so that we can bump that up. You can find the margin of error by the big number minus the small number divided by 2. So I could find the margin of error by doing my upper bound and then our lower bound, and I want to subtract those. So I'm just going to go to right here. I'm going to grab the upper. Grab the upper here, copy, paste, minus the lower, just double clicking to copy, paste, and then I want to divide all this by 2. So I'm going to, at the end of this, do a close parentheses, which actually will add an open parentheses at the beginning, and then divide by 2. And so notice how I get my same margin of error that I had down here. You could have done this in using this coding that Desmos has. So I could copy and do, copy this lower minus the upper. Notice how that works with that function, but that's a bit weird. I like just to use the numbers. Or the other way, the last way that you could do to get the margin of error would just be kind of probably the most obvious way, is take one of your bounds and subtract it from your point estimate. So let's do the upper, and then our point estimate is 0.42. So if I do this number minus 0.42, that's probably the most direct way to get the margin of error. So that's why being able to pop those out might be helpful, so you don't have to worry about weird rounding. All right. I then have a follow-up question. Let me make this big for us. This says, oh, I'm breaking things now. This says, alas, that data didn't convince me to produce these pins. So now suppose I took another random sample, but this time asked a larger amount of them with a larger confidence level. So I'm increasing my sample size, which should decrease my interval, but I am also then increasing my confidence back up to 95. So in this sample, I have 150 of my customers. Again, random sample, 68 of them said that they would buy at least one of these pins. Let's make a 95% confidence interval. So let's do this same process. We should get an interval from about 37% to 53%. Notice this interval does not contain 33. It's actually fully above 33. So then we would kind of have evidence to think, oh, it's probably I was rambling, sorry. Um, should me, this business owner, should I then probably go ahead and finish designing this pin and produce it? Yeah, if this was true. Because then more than 33% of my customers would want to buy this pin, and that was kind of my goal. And so then I would feel safe to do that. All right, so let's go to Desmos and do that. So we have this information. So maybe if you want to do this on your own, follow through with that process redo what we just did, but using this information to get a 95% confidence interval. I will pause and wait. Hopefully you've paused the video and you've done it. All right. So we could just edit this because notice that this says successes and sample size. So I could just change my successes to be 68 and my sample size to be 150. And then I'm going to change my confidence level to be a 95. And that's how we can get our confidence interval. Is that where we got when we did it by hand? Yep. Or maybe you don't want to do that. Let's just do a new inference procedure. So add an inference, go to z-test rather for proportions. Then we're going to pick successes. We had 68 and 150 and press create test. Open up our confidence interval, make sure it says 95. That is what it is by default, and we get the same thing that we had a second ago. All right, so with this, then I would be, like I said, I should produce this new pin. All this kind of confidence interval stuff sounds a little bit like a hypothesis test. I'm going to go ahead and move on and show you how you could use this process to do a confidence interval. If you're like, I misspoke, do a hypothesis test. If you're sitting there going, what is a hypothesis test? Then maybe come back and watch this video in the next chapter. But if you're ready to talk about the hypothesis test, let's go. So we're going to recall the small inconclusive sample. Let's go back to that. Let me change my values here back to 21 successes out of 50. I'm going to close my confidence interval, and we're going to take a look at the significance test. So here I have the full work on how we could do this by hand. Let me make this big real fast just to walk through this. So we're going to perform a hypothesis test at the 5% significance level to see if there's convincing evidence that more than 33% of my customers would purchase my new pin design, and let's assume that all conditions are met. So my null hypothesis is that P is 0.33. Depending on the class you're in, like my current online stat course, that book, which I hate, does this to the null hypothesis. They would do a less than or equal to, which is fine. That's just not a thing I typically like to do. So either the null is that P is 0.33, or maybe you might be following a course that does P is less than or equal to 0.33. Either way, notice the equal part is in the null. The alternative is the same. The alternative is that P is greater than 0.33. Notice my null hypothesized, my null parameter value, which we shorthand often as P sub null or P null, is that 0.33. That's the value that I'm putting to the test. So it's like, I've said, I would be convinced to do this new pin if more than 33% of my customer base would buy it. And I found a sample and I got 42%. Well, that's cool. That's more than 33. But is that just dumb luck that I got more than 33? Or do we think that that's statistically significant, meaning not likely to happen by random chance? So that's why we compare. That's why what we're doing is if we take a look at the standardized test statistic, that typical idea is we take a look at our stat, subtracted by the null parameter, and when I do that, I get a difference of that 9%. Well, is 9% odd? Well, it kind of depends on what our sample size is. With just 50 attempts, 9% might not be that odd. Turns out that our standard error, using the 0.33 this time, because we use the p null, we should see about a 6 or 7% wiggle from the mean. That's the typical amount that we would expect. And so that 9% isn't too terribly odd. It would have a z-score of 1.35. So it's 1.35 standard errors above the mean is how unusual that 9% is. And so then we just then do a normal distribution with that. Um, if if the mean is 0, standard deviation is 1, and we get 1.35, how likely is it for us to get a value equal to that number or bigger by dumb luck? Turns out it's about 9%, about 0.088. Or if we leave it at the null of 0.33 with this standard error, how unusual is 0.42? That same thing. So recall our conclusion here is that our p-value 0.088 is greater than our alpha of 0.05. So we failed to reject the null hypothesis, and then we don't have convincing evidence for the alternative. Alternative being that the actual proportion of customers who would buy my new pen is more than 0.33. So I don't have evidence that it's more than that. I know our sample showed that it was more, but that seems like it could be more likely maybe just due to dumb luck that it was that high. So let's show you this process using technology without having to do all this math business. So I'm going to hop on over. Let me keep this up for a second. We have the Z prop test that we did. Actually, let me just start over. So let me do our inference. We're doing a Z test for proportions. We're putting in our 21. We're putting in our mean of 50. I misspoke. We're putting in our sample size. Why do I keep saying things wrong? We're putting in our number of successes, which is 21, and we're putting in our sample size of 50. There we go. Let's press create test. And then I'm wanting you to do this time a significance test. You can view them both, but let's just focus on the significance test. Again, Desmos wants to do something. It wants to show you that it's able to do something and provide you the example of how to do it if you want to change it. So do you see how 0.05 right here is grayed out? They've put in a default value of 0.05, a default value of 0.5. So what we want to do is change this to our 0.33. So when we do, it gets updated. Our tails, we want to do a greater than alternative. So notice our tails, it could be to the left, it could be to the right, or it could be in both. Both would be the two tail. This would be less than two tail, right tail. So let's just do the right tail approach. And so we have our Z is 0.1353, which we found by hand over here. And then our p-value right here is 0.088. So this shaded region, this is 0.088, which we found over here. Notice how our pictures match. If you want to see a few more pieces of information, click on the three dots. Actually, it's not quite giving us all the information. I was wanting the standard error, but it doesn't do that for us. But it gives us the z-score and p-value again. So if you want more decimal places, you can do that. Same thing as before, you can get a lot more decimal places here. Or a really interesting button is this, export significance diagram. Let me get rid of my iPad, and I'm going to click this, export significance diagram. When it does, it will graph the normal distribution if the null is true, centered on our with the standard normal here. So what we had on our what we graphed earlier in orange here with the mean of 0, standard deviation of 1, that is what this is graphing. A normal distribution, mean of 0, standard deviation is 1. It's using Z1. This Z1 is being our test score here, our test statistic, and it's finding the right tail greater than that. So it's showing you that picture, which is the same picture here, but that way if you wanted to do something with this or adjust it in some ways or look at it more up close, you're just kicking this picture out so that way you could look at it. All right. So that's that one. Let's switch and do the other one. So now what about for the larger one that is conclusive? I accidentally had the small inconclusive. I forgot to update that text. So we're going to do a similar thing, but this time with our 150, our sample size of 150 and our number of successes being 68. So let's go through that process. And let's see what our p-value would be there. So let's open up our inference. Again, z-test for proportions. we're doing 68 for our number of successes. Sample size 150. Say create test. Toggle open significance test. Again, Desmos wants to be helpful, so it puts in our 0.5. And then I can put in our 0.33. This is, oops, I missed our 0.33. I knew that it was broken because it was red and these things were saying undefined, so I knew something was wrong because I needed it to be a 0.33. I want the area to the right, so let's click right. And then, so I see that this z-score is 3.212, which I have on my iPad. And then a p-value 0.007, which I have over here, which is super duper duper tiny. Again, if you want to see those values with less decimal places, sorry, with more decimal places, you can do that here, even more right there. And then you can also export the diagram so you could see the picture. We can see that, oops, let me get my iPad to go away. So when I open this up, we can see that it says it's really small. I don't even see the shading. So I'm going to come over here and actually just zoom in until I can see the shading. And oh, look, it is there. It's just really tiny. So here with a z-score of 3.212, which is where this lies here, it's really, 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 really tiny. I can zoom back out by clicking on this zoom fit here. And so then that shading is so tiny, I don't even see it at this stage. I can't even see any of the shading, but we just saw that it was there. So then in conclusion, that p-value 0.007 is less than our alpha 0.05, so we reject the null, and we do have convincing evidence. In fact, I could have probably said we do have very convincing evidence because that p-value is very small. Very convincing evidence that the actual proportion of customers who would buy my new pen is more than 0.33. All right, so I hope this helped show you how to use Desmos's new inference. We can do confidence intervals. We can do a hypothesis test. It's pretty intuitive once you know how to add it in. Hope this helps. I'll see you in the next one. Bye.